Welcome to Calculus. I'm Professor Geist. We're about to begin Lecture 11 on differentiation rules.
From your previous exposure to calculus, you probably learned how to compute derivatives quickly, without the definition, by following a certain set of rules or laws. We're going to cover those rules in this lesson. Such a topic has the potential to be boring, but pay attention because we're going to cover why the rules hold. And in doing so, we'll get a better grasp of the notion of a derivative.
Recall from our previous lesson that we had two different ways of defining the derivative. One is in terms of a rate of change. It's a limit as the input approaches A, the change in the output over the change in the input. Our second definition, a little bit stronger definition, is in terms of first-order variation. One changes the input to f by a small amount, h, and looks at how the change in the output depends upon h. If you like, it's the coefficient of the first-order term in the Taylor series of f at a. From these definitions flows the interpretation of the derivative as the rate of change of the output with respect to change in the input. And this is the interpretation that you will want to have memorized. A few remarks are in order. First of all, the derivative, as you know, most certainly depends upon the input value, A, that you are examining. Secondly, a derivative concerns rates of change. We're not actually measuring how much the output changes. We are looking at the rate of change as the change in the input is getting closer and closer to zero. Lastly, the derivative at A is telling you a rate of change. It's telling you how fluctuations or changes h in the input are perhaps amplified if the derivative is positive and larger than 1, or damped if the derivative is, say, less than 1, or reversed in the case where the derivative is negative. That is a good interpretation for the derivative, one that will serve you well in this course. Now, there are several rules associated with computing derivatives. I'm going to present these rules compactly using a simplified differential notation that you're familiar with from your previous exposure to calculus. The first rule is that of linearity. This consists of two parts. First, what you might call a summation rule, that the derivative of the function u plus v is the derivative of u plus the derivative of v. The second part of linearity says that if we multiply u by a constant c and take its derivative, what we get is that constant c times the derivative of u. The second rule, the product rule, states that the derivative of the product of two functions, u and v, is u times the derivative of v plus v times the derivative of u. Lastly, and perhaps most importantly, the chain rule states that the derivative of a composition of two functions is the product of the individual derivatives. We'll have some more to say about that in a moment. For now, let's focus on the rules of linearity. The summation rule can be visualized rather simply. Keeping track of how u changes and how v changes, and keeping track of how u plus v changes, is really not that difficult. Likewise, when you multiply u by a constant, what happens to its rate of change? It is similarly scaled. That picture is at least reasonable. There's another way to think about these rules as well. This is a way that I often think about it. If you take the sum of the two functions and then differentiate, it's the same as differentiating the pieces and then adding them together. Or likewise, you can multiply by a constant and then differentiate, or you can differentiate and then multiply by a constant. Whichever path you travel, you will get to the same place. These pictures illuminate, but do not really justify, the differentiation rules. To do a better justification, let's use our definition of the derivative as a first-order variation and employ the language of big O. First of all, u plus v evaluated at x plus h means what? Well, we take u evaluated at x plus h and add to it v evaluated at x plus h. Now, by our definition of the derivative of u, we know that the term on the left is u plus the derivative of u times h plus something in big O of h squared. Likewise with v. Now, let's rearrange this sum by ascending order of h. The 0th order terms are u plus v. What are the first order terms, those that have an h? Well, on the left we have du dx, and we add to it the term from the right, dv dx. Everything else is something in big O h squared plus something in big O of h squared. That is in big O of h squared, naturally. So we see that the first order coefficient is the sum of the derivatives, as expected. Likewise, when you multiply u by a constant, c, and evaluate that at x plus h, it is simply c times u plus du dx times h plus something in big O of h squared. The 0th order term is c times u. The first order term is c times du dx times h. Everything else is a constant times big O of h squared. But remember, in big O, constants don't count. And so we see that the first order term, the derivative, is c times du dx.